On the response and recovery side of disaster management, at times the severity of hazards and disasters makes it logistically challenging to send in human operators. Under such circumstances, we can embrace the possibility of deploying rescue robots and drones to navigate dangerous terrain and aid survivors. These autonomous drones and robots can also play a pivotal role in the provision of emergency equipment and medical or food supplies in hazard environments, while also being able to replace rescue personnel in carrying out search and survey operations. There is a growing interest in developing disaster robots that can be deployed in place of personnel, as it can greatly improve the overall safety and security, as well as efficiency of disaster recovery operations to reduce human, structural, and economic losses. Despite its promise, the in situ operationalization of robotics during disasters remains a challenging proposition. Today, we have 4 distinguished speakers who have successfully been able to put this into practice. We will invite the first panelist, Dr. Robin Murphy, who is the Raytheon Professor of Computer Science and Engineering at Texas A&M University, and a director of the Center for Robot-Assisted Search and Rescue. I've had the pleasure of moderating another session with Dr. Murphy on the panel a few months ago. As she's one of the pioneers of the field of disaster robotics, I look forward to gaining more insights from your presentation, Dr. Murphy, today.
Well, thank you very much for having me here. And if you could just confirm that you can see my slides.
I can see them.
Excellent. Well, it's such an honor to be here with such great researchers and practitioners. I'm going to talk a little bit more to frame how robots save lives in disaster-hit areas. And just to go through my background is that I have been working in disaster response since 1995. And as part of the Center for Robot-Assisted Search and Rescue, we have deployed to over 30 disasters in 5 countries, as well as trained emergency managers. Our group focuses primarily on emergency managers and government agencies, less on NGOs and relief side, for reasons you'll see as I talk later. When we think about robots, everybody has their own view of what a robot looks like. We work with small ground robots that fit into backpacks, things that are highly portable. We work with small, inexpensive aerial systems, both rotorcraft and fixed wing, and marine-based vehicles, both ones that go on the surface and those that go underwater. So we'll refer to those. And these type of robots have already been used for almost every disaster and every objective you can think of, from flooding, earthquakes, tsunamis, chemical spills, building collapses, pandemics. So all of this is part of that all hazards emergency managers need to deal with. And so these robots have been used. So do robots save lives? Yes. Less directly, but directly, for example, unmanned marine vehicles during the Syrian boat refugee crisis in Greece, that what looks like a floatable life jacket was responsible for saving at least 26 people trapped against the rocks and high seas in a place where the Greek Coast Guard could not get to them. So robots also save lives, probably more commonly indirectly, by assisting with tactical operations, assisting with strategic planning. For instance, in a recent hurricane down in Louisiana, until we flew drones, they didn't realize a particular area was very hard hit, nor how to get in, what roads were still open. And another way of saving lives is by accelerating economic recovery, which includes medical consequences when your hospitals are down, when you can't get insulin, when you can't get critical medicine. So that's an important aspect of robotics. But it turns out saving lives is not really the robot's real function. The real function depends on where we are, what phase of the disaster, and who's deploying the robots. So if you think about, there's lots of ways to think about disasters. There's several models. Let's just go with there's stuff that is before the prevention and preparedness, then you have the event, then you have the response, and then you have the recovery. And what becomes important to know is during that response, when people's lives are directly in danger, that's handled by formal emergency management, by governments and their representatives have special training. In most countries, there's a temporary suspension of some rights. You can trespass, you can do stuff, you can arrest people for interfering, no questions asked, those sorts of things. And you also don't have a lot of volunteers. But during recovery, which usually is when people evacuate or now coming back, the government still does things, but now you have insurance agencies, related businesses doing waste management and removal, things like that, and humanitarian relief efforts. During that response phase, you see quite a bit different, patterns. So wide area disasters like hurricanes and earthquakes, flooding, the emergency managers typically know where people are likely to have been. They're really more focused on the tactical operations of getting to them, locating in terms of not only just there, but finding them, but how to get to them, and also the extent. Structural collapses, one of the things you'll see is that dogs typically indicate that they're survivors, but they can't tell you where because it's air, it's not really there. So then you use cameras and robots to locate and also help the structural engineers try to help remove more quickly the debris to get somebody out, which usually takes about 10 hours. So having a robot being able to look on the inside of that pickup stick pile of debris can help. And then you see telepresence is used heavily during Fukushima, as well as currently for the last 2 years for pandemics. The recovery phase, this is where you start seeing agencies begin to shift from life-saving and mitigation to documenting damage, doing a lot of mapping, inspecting critical infrastructure, getting everybody back in, getting businesses back. And also you see continuing to handle surge we saw in public health with the pandemic. But let's not forget the incredible value in saving lives in the future by preventing and being prepared. And so you can see a lot of establishing what is the digital elevation, what is the likelihood, what is the fuel in this particular area that will lead to a wildfire, and also identifying evacuation routes, monitoring during a flood. Floods usually don't happen overnight. They build for several days, and being able to monitor that. So those are some things. But let me conclude with responsible robotics innovation. One of the things that we've explored and created models for is how do responders decide to use a particular robot technology? Like Bilal said, this is a disruptive technology, even though it's been around since 2001. Well, the first thing is that they are not very open to innovation pushes. That's a demand pull. They have actual needs. And I think you'll see some beautiful work. Fatima will be talking about working with CAL FIRE. We're really working with them rather than us telling them what's there. Is very important. The second thing is suitability. Does it fit their particular task and objectives and their constraints? Often are costs, particularly in developing nations. And you can see that everything we've been able to do since Hurricane Harvey has been with drones that cost on the order of only $1,000 US dollars. Likewise, those marine vehicles, the Emily ones, those are $10,000. So those are very affordable, even for underdeveloped countries. Ground robots are more expensive. They just are, but they probably already exist in the region for bomb squads. And then the third factor is risk. You don't want to make situations worse. We had a mine explosion where they sent in a robot and it blocked absolutely everything. It failed in the worst possible place. So typically you're going to see the responders use commercial off-the-shelf systems that already exist, already work for sewer inspection, the drones that are for construction work and all that, and repurpose them for their particular mission. I do want to also make you aware of 5 unethical syndromes, both if you're a roboticist, we kind of accidentally fall into this, and for you as possible adopters. One is there tends to be a bit of disaster tourism. Let's go check it out. We have that. I got a call after Surfside with some researchers that, oh yeah, this would be a great time to try this human factors thing. It's like, no, it's actually a disaster. Pet project. Oh, my robot just is perfect for this. And you see a lot of this innovation push, and that's particularly, it insults the responders because they know what they need, right? And it's a very, quit telling us what we should do. So that, and then they get very testy with all roboticists. There's a fear of missing out. We saw with the pandemic, some uses of drones that work great in China, which has a very different set of issues, cultural expectations than we see in Italy and the United States. And the public accountability, the reaction was quite different. So be aware of that. Something is not necessarily better than nothing. I had a lot of roboticists say, oh, something's better than nothing. Nope, it's got to work. It's got to work. You can't make the situation worse. And if you make the situation worse, or if the robot fails, it gives everything in robotics a bad name with emergency managers. And then there's that hidden agenda. I've seen this a couple of times, fortunately not that often, but it does happen. It's the data. Oh, I'm going to get lots of data. I'm going to get this. And so be careful, make sure it's clear that all the data belongs to the agency and then is released according to their procedures to save for privacy. So the big takeaways are, remember, most of the life-saving activities are done by formal emergency management. Robots are not really replacing what people can do or routinely do. They're doing things we can't do, or doing things that we don't do very often because it's too expensive to use manned aviation. Cost isn't a barrier to adoption, but awareness, suitability, and reliability are. And those syndromes, just be aware of them. But the big thing is we should all be working together. And I applaud the UN and the AI for Good initiative and hope we can work together on this. Thank you.
Dr. Murphy, thank you very much for your outstanding presentation. It's definitely enlightened us on a new facet of disaster robotics, which is of extreme importance, the human-robot interaction. While we envision the implementation of these frontier technologies, we also need to keep in mind the cost and the ethical aspects, as you mentioned in your presentation. Perhaps to elaborate further on this, I'd like to call upon Professor Howie Chaussette, Carnegie Mellon University, as a leading expert in multi-robot systems. He has donned many hats. He's the co-director of the Biorobotics Lab and serves as a founding editor of the journal Science Robotics. Professor Howie.
Thank you. Can you hear and see me?
I can see you, I can hear you.
And I'll share my screen. All right, wonderful. Yeah, I want to, stress, a couple of points are made. Robin, really makes this point that, we are here developing tools to assist rescue workers in their task, and that's our role. It's a great role, but that's our role. And again, it's a team effort, and sometimes understanding, at least for me, I think we all want to be team players, but how to be a team player also is part of the lessons. And at the very least, I should compliment Robin for me, introducing me to that world and how to become a better team player. So the thing my group is famous for, I think most recently, are these snake robots. And this video is a little jerky, probably because it's going through the internet, but they're cool systems, and what they can do is they can use their many joints, their many degrees of freedom, to get into tightly packed spaces, therefore extending the reach of rescue workers. And I might add also, perhaps if they move in a minimally invasive way, elevating the safety of victims who may be in a collapsed rubble. What you see there in the upper right corner is one of my students, Julian. We were invited by the Mexican Red Cross in 2017, and I saw there's at least one person from Mexico City, Sylvia. So I hope no one close to you were poorly affected by the earthquake. I hope so for you. But the robots, we went in and cleared a couple of buildings. But this video here, really shows off just how big a problem this is and how unprepared we are. We being the researchers, for God's sakes, we're using a bucket to block the sun from our computers. But we did go down with what we had. Now I should also complain for a second that as many technical challenges and problems there are, there's also a money problem, and frankly, this kind of work, and maybe I'm biased, doesn't get the support it deserves for lots of reasons, but we can discuss that later. This is a new snake robot that we built that is pretty maneuverable and goes underwater, and you can see it's performing all sorts of acrobats. However, this video is a lie because the controls aren't really well thought out yet, and the water is clear. When we put this in one of the rivers here, it was pretty clear that you have to do more with mapping and sensing perception, as well as the user interface, upon which all those other technologies require. So I'll get back to this snake robot, and I'll just ease us into why this is a hard problem. This is pretty cool. There's the robot executing all these gates, and we're able to do all this in real time, and we're so proud of the result. But here's one of the big fat lies that people do in snake robot demos. They operate the robot in regimes that a wheeled vehicle can do just as well. You want a snake robot when you're on this unmodeled terrain, hard, and I might add highly confined. What's happening here is, in addition to the dimension reduction techniques that we developed, we're now applying, or we've developed admittance controllers that wrap around these low dimensional representations, so a person can steer the head of the robot as if the person is driving a remote control car on flat ground, and the robot figures out how to coordinate its joints and adapt to the unmodeled features of the environment. Because let's face it, we're not going to know in advance what's going to happen. So that's topic one. I'm going to assume the moderator will just cut me off when I run out of time. But I just want to mention quickly topic two, and that is, when there's a broad area disaster, so the snake robots were good for very fine, narrow. Now, when you're in a broad area, what you need to do is find signs of life as quickly as possible. And we roboticists and AI researchers naturally think, let's send out the drones and the other vehicles, but we could also have ground vehicles as well as people to go acquire this information. And this just opens up a whole host of interesting problems for us academics to solve. But again, the goal is to supply the rescue workers, the first responders, with tools. But at least this highlights why academics and small companies, should be involved in this part of development. Now, here's one problem that I've been working on. It's based on ergodic search, and it's something that I'm trying to really figure out, how to do right now. But essentially, you have an information map, like where the gold is where the high likely locations where people are, and you have another distribution that describes how your robot moves. And what you want to do is drive those distributions to be in equality so as to maximize the likelihood of finding signs of life, or use the information as you discover it. Our first contribution to this was developing a means for having heterogeneous agents. In other words, aerial vehicles flying over and ground vehicles or people on the ground looking around, playing to their strengths of their sensing and their motion capabilities, but doing this in some provably optimal way. Is new, and this is the work that we want to continue. One of the two projects I have with Robin right now is dealing with this so-called curse of dimensionality, because you still have to send all these robots out to go find signs of life. And the thing is, in robot planning, and again, there's tons of problems: perception, localization, communications, tons of problems. I don't want to give you the impression this is the only one, but the one that we've been thinking about is when you have one robot, a planning problem is so hard. 2 is twice as hard. 3 is 4 times as hard. 4 is 16 times. It grows exponentially. And what we've done is we've developed these techniques that take existing graph search approaches like A-star or constraint-based search. And we were able to sort of beat the curse of dimensionality. We have growth that is lower than exponential. So in fact, this video you see here on the right is actually 200 robots planning a path start to goal. And there's not enough computation on the planet to perform this search with this conventional techniques. Both our approaches, you can do all this quickly and I might add in real time. So I'll finish there with some video. If I wanted to show this video. And just to highlight that, if you looked at the snake robot, you would see it's modular, and we're also starting to advance the architectures for modular systems as well as the science of modular systems. What we want to be able to do is have the rescue workers just show up with a bag of parts, take out a camera, take a picture of the scene, and then we have a system that will suggest what robot that person needs. And as simply as putting together Lego, create the robot, hit a button, and then the rescue worker has a tool to extend her or his sensory reach. And what you just saw there was a live swap out of a leg for a wheel, which is pretty cool because it's live, everything's on. And I note it's the same controller driving that robot. So the robot figured out on its own, oh, I have a wheel now. It's not a leg. And off you went. Just like when you plug your keyboard into your computer, nothing drastic is happening to us, but under the hood, there's a lot going on. All right, so the 3 things were the snake robots, mobility challenges, high dimensional search, and then a new cool thing in modularity. And with that, I'll stop and pass the baton to the next person, or if someone has a question, happy to answer a question.
Great, thank you, Professor Howie. That was a really inspiring and insightful presentation. Very cool snake robots and modular robots at the end of your video. We'll come back with questions later on after all the speakers. I'd like now to invite the third panelist, Professor Davide Scaramuzza, University of Zurich. He has undertaken trailblazing work in the domain of autonomous drones and has worked closely with the United Nations International Atomic Energy Agency. Davide, the floor is yours.
Thank you, Bilal. It's really an honor to be here with you guys today. So I've been now working on autonomous navigation of drones for about 12 years, and I specialize on drones that can navigate using onboard cameras and onboard computation without relying on any link with the human pilot. So if you look now at commercial drones today, so nowadays, drones are already used in disaster response. And one of the main applications, like Professor Robin Murphy outlined at the very beginning of this webinar, is actually, the main use case is actually for situational awareness, where the drone is actually deployed and then is used as an eye in the sky to get an idea of the extent of the disaster, be it a fire or a flood or anything else. Here you can see an example, a company from Switzerland, which actually started from a lab 6 years ago. It's called the Photokite. It's a tethered drone for first response. And tethered drone means that actually the drone is attached by a cable, so a tether, to the firefighter truck so that it can receive electrical power over the tether. This allows basically the drone to fly almost indefinitely, so for many hours. And also it allows also the drone to use the tether to stream images using standard cameras or thermal cameras that can then be used by the search and rescue teams to identify things from the air. But as our first 2 speakers pointed out, the key challenge for today's search and rescue robots is actually to get them into the rubble or even in the wilderness. So what you see on the left is an image of the Miami building collapse during this summer. And on the right, you see a random forest. So these are 2 typical situations where actually, drones need to be deployed to get an idea of which people are actually, where people can be found inside the building, where are they lying, so that basically the search and rescue teams can actually maximize their action later. And the problem is, though, that if you rely on all commercial drones nowadays, the problem is that they are still relying either on a human pilot or on GPS-based navigation. So how do humans typically control drones? So humans typically control drones either by a direct line of sight. So you observe the drone directly with your eyes in the sky. And the second way is to actually use a camera that streams onboard video to some display worn by the pilot. The problem with this video streaming is that typically you can only go up to a few hundreds of meters or kilometers, depending on how many obstacles there are between the pilot and the drone. For example, if you are navigating under line of sight, you can go up to 6 or even more kilometers. But if you navigate in a forest, this actually drops to a few hundreds of meters. And if you want to navigate a drone piloted by a human inside a building like Fukushima-like, actually the range drops to a few hundred meters, because actually the wireless signal becomes very weak, especially when you have several concrete walls between you and the drone. Now, so what we would actually need is a drone that can operate without a human in the loop. So what we would call actually level 4 autonomy, at least. So a drone that is almost fully autonomous. So basically the human only sends the go command, and then the drone accomplishes the mission without any human operator. The problem is that when you now look at commercial drones that are fully autonomous, they're actually still mostly relying on GPS. And the problem is that GPS works as long as you can actually, receive the signal from the satellites. So it doesn't really work indoors. And it can actually be very unreliable, even outdoors, especially if you are under the tree canopy or even close to structures. So now from this, what are, in my opinion, the key requirements for autonomous drones for search and rescue operations? I think, in my opinion, what we will need is actually drones that have not a fixed shape, but actually have a morphing shape, similar to the snake robots of Professor Choset. Also, we will need at least a level 4 autonomy, so the drone flies without any human input, similar to the most modern autonomous cars. But also they need to be fast. And finally, ideally, they should also be as small and lightweight as possible in order to actually enter very small holes and even rubble at some point. So let me go through some of the work that we've done to address some of these key requirements. Let's start by talking about morphing shapes. So this is actually work that we developed with Professor Dario Floreano from EPFL in 2018. This is actually our foldable drone. So it's a drone that can change its shape depending on the apertures that it has to pass through. So as you can see here, it's during a simulation exercise in Bern. So during a simulation of a search and rescue operation in Bern. The drone is fully autonomous. It uses a single camera and an onboard computer. More about this later. And as you can see in these other videos, the drone can change its shape depending on the type of aperture that it has to pass through, or on the type of surface that it has to inspect. Now, what is the idea? How does it work? So in this graphical illustration, you can see different modus of operandi of the drone. So when the drone actually flies in free space, either outside or inside, then it's relying on the basic configuration called the X configuration. So all the arms are fully open in order to have the maximum possible stability in flight. Now, if you want to pass through a horizontal gap, like the one I'm pointing it with my mouse, then you may want to assume an H configuration, so-called because it looks like an H. You see, basically you extend the two front arms in order to squeeze through a small aperture. But for example, there might be apertures where actually it's more convenient to fully fold all the arms, like for example, the aperture here on the ceiling. And then in this case, you would actually fold all the arms in order to get the smallest possible shape. So I think this actually could be something that could be used by drones in order to be able to access buildings that would be difficult otherwise to access through the conventional ways. Another thing I want to talk about is autonomy, at least level 4 autonomy, which means drones would actually need to fly completely without any human input. So that actually requires that the drone has some sort of sensors, for example, cameras in this case, in order to perceive the environment around the drone. In this case, you see that the drone is actually endowed with the 2 stereoscopic cameras, and then also some sort of brain, so an onboard computer that actually computes, processes all the images produced by the cameras. And another requirement that we would actually need is that the drone is also fast. Why fast? Well, first of all, because in search and rescue operations, minimizing times actually translates into minimizing casualties. But also there is another more important reason why we want to be as fast as possible, because also it would increase, so flying fast would increase the range of drones, because of course you cover larger distances by flying faster and faster. Of course, so some people would argue, yes, but by flying faster, you also consume more battery power. That's correct. But at some point, what happens is that there is still, you know, an optimal speed that is larger than 0 that would allow the drone to actually maximize its range. And that's exactly what you see in this plot over here. So there exists an optimal speed that would actually guarantee to cover all the largest possible distances with the same battery power. And let me show you some progress that we are making in navigation in the wild, so in the wilderness. This is actually work that we recently published in Science Robotics, where we developed an algorithm that allows a drone to fly very fast, up to 40 kilometers per hour, even faster than commercial drones like Scadio, especially in very cluttered environments like forests. And we could do this also in foggy environments or low light environments. The problem when you fly, especially so fast and in different environments, that as Robin Murphy said at the very beginning, is that you need tons of data. Now, we are relying more and more on simulation to actually train these algorithms, because simulation is fast, it's cheap, and especially safe when you actually try to train these algorithms, because training means you need to tune the parameters of all the algorithms. And so we are actually putting a lot of work on trying to develop realistic simulators that are not just photorealistic, but also physics realistics. Another thing I want to talk about before conclusion is actually also small and lightweight drones. And this is more farther in the future, but I think we all agree in all these presentations that you know, in the future, we would like to have a very small robots that could actually enter into the rubble. And so this is some preliminary work that we did with Professor Luca Benini from EDH about trying to actually optimize some of the algorithms that I demonstrated before for larger drones in order to run on smaller drones. And the drone actually you see here, it's a Crazy Fly drone from a Swedish company that weighs less than 27 grams and has a diameter of less than 8 centimeters. The problem with such a size is that actually you cannot really squeeze all possible computing power on such drones. So actually we are relying on very small computers that consume very little power. In this case, a 64 milliwatt computing power. The problem is that you cannot run every possible algorithm, so you will need to actually make some optimization to make it work. But again, as I said, it's actually more farther in the future. And thank you for your attention, and especially I would like to thank the people behind all this amazing research, which are my students. Thanks a lot.
Thank you very much, Professor Scaramuzza, for your presentation. Very interesting to learn more about the application of these micro UAVs for the management of man-made disasters too. We will now move to the last panelist, but not least, before we commence our discussion. I'd like now to give the floor to Ms. Fatma Hamdani, co-founder and CEO of KH Aerospace. In this role, she has been spearheading the work relating to the leveraging of UAVs to save lives and engage in disaster relief activities. Fatma?
Thank you, and Davide, this was a great setup for what I'm going to be discussing next, because I think, Davide, you focused a lot on the rotary or the quadcopter world of the drones. And as we go into the other side of this, where if I do an analogy where you have a helicopter and a plane, I'm going to focus a little bit more on fixed wing unmanned aerial platforms, or UAVs, which are the equivalent of aircraft planes versus the quadcopters or the helicopters of the drone world. So as an organization, we are a triple bottom line organization. For us, profit, people, and planet are equally important. And that's why taking a look at the various aspects that the UN has brought up, specifically from a disaster management perspective, wildlife anti-poaching, looking at what were the issues that exist and how can we solve for them was one of the core components as we started building out our technology. So when we started, there were 4 massive issues. When you look at UAVs, unmanned aerial vehicles, as Davide pointed out to a few of this, I'll go into details of a fixed wing and why this is extremely important for disaster management. One is how far the UAV can travel from the operator. As Davide said, if you only can travel up to line of sight, then in that case, you are limited to where you can operate. So how far the UAV can travel from the operator was one of the limiting factors. How long it can stay up in terms of endurance. So if you send a UAV out, it can only fly for 90 minutes and come back. What are you going to do over the disaster? And I will be sharing a presentation that goes over some of this once I lay out the 4 issues and then kind of go into details around that. The third aspect is integration. Why are we flying these robots? Essentially to do monitoring for communication. So integration with payloads, sensors, radios, and an open architecture that allows for rapid plug and play was the third issue. And the final issue is operational efficiency. If you need a team of 25 people trying to operate one single UAV, it's not going to be tactical. It's not going to be relevant from an operational perspective. You might not have anybody in the cockpit, but it's not unmanned. And so those were the 4 massive issues that we were trying to solve for when we started the organization. And that's what today we have actually solved for. And that's where the relevance comes into. So I'm going to share my screen real quick. 1 second. And so today we are flying the longest endurance unmanned aerial platform in its size and weight category in the world. So essentially what that means and how does that translate into what we're talking about? Beyond line of sight, fully autonomous asset that allows for plug and play. From the point you hit go, it can completely complete its mission without any human in the loop. The longest endurance that we have flown today has been nonstop 26 hours, and this can extend up to 340 hours. So that coupled with a lot of the technologies that we're talking, whether what Davide mentioned, Howie mentioned, Robin mentioned, you truly can get persistent eyes on a particular disaster-stricken area. But how we look at disasters is in different stages. The first stage being the stage that essentially, and I'll come back to the UAV itself, is actual monitoring. Is there a way to avoid the disaster before it becomes a disaster? And so from that perspective, the ability to fly beyond line of sight persistently, nonstop, for long durations allows you to cover large areas, whether that be Kruger National Park or whether that be the hotspots in California or Colorado or the ocean, so to speak, so that you're scanning constantly for potential issues that might arise. Could a spark that the PG&E line that led to the fires in California, could that have been detected early on? Absolutely, there is a possibility of that if you're flying persistently and cost effectively and efficiently, right? And that's where all of this comes in. Also, because our asset is 100% electric, you're able to fly it at different altitudes, starting with the couple of thousand feet above ground level, going all the way up to 20,000 feet above ground level. And you'd say, why is this important? One of the other components that Davide brought in is airspace. And how are you maneuvering in a crowded airspace, whether that be aircraft, commercial aircraft, other assets that are flying? One of the only ways that FAA is going to allow these assets to fly fully autonomously is airspace deconfliction. And so whether that be through ADSB, which is airspace deconfliction components that are integrated into these assets have to fully autonomously figure out their space and everything else that's entering their space. And we've done that. So one of the key components that we do is constantly monitor environmental conditions. We build 3D models of what we are flying within, whether that be to detect a thermal, the hot air rising up from the ground, the center of a thermal for flight and endurance, or whether there is a mountain range that is happening for avoidance, or there is another aircraft that is within our vicinity that we have to sense and avoid. So all of those components are built in from a fully autonomous asset and platform perspective. So let's talk about initially, how do you actually monitor to ensure that you're doing early detection and avoiding disasters altogether happening. In addition to long endurance, what's key is edge-based computing. So today, the asset is able to detect and is able to earmark objects, whether that be fire, humans. And so if you're able to build those models on board and are able to flag changes, are able to detect and also further train the machine learning algorithms in the back end, so that if there is a change detection that is happening, you're able to feed that back and bring the human back into the loop if needed, when needed, versus just sending in the video feeds, which would clog up some of the bandwidth, depending on where and how you're flying and you're doing backhaul of data. So essentially, starting with the first phase of a disaster, early detection and avoidance, and being able to very effectively pass that information back to first responders to be able to respond back. The second is actually, and I'm taking the example of aerial fire response, because there are components. Today we have folks that are flying manned aircraft over smoke. It's highly, highly dangerous to do so. Whereas if you have an asset that is able to fly over smoke fully autonomously, is able to detect how and where things are progressing. Also, as we start collecting and meshing information and sensor data, you're able to detect where the wind is blowing. So you're able to predict, in some cases, where the fire will progress. And that is how you also save some of the first responder lives that get compromised when they are in the way of a fire. So these aspects of being able to do that from an aerial perspective, be able to fly over dense smoke, detect other heat conditions so that you know how the heat is progressing, is extremely important. In addition to all of that, we were sitting with California Fires and California Emergency Services. And one of the things that they brought up, they're like, our first responders move with 5 pieces of communication equipment onto the ground, when they're actually doing fire protection. And even then, they lose comms. When the disaster in Puerto Rico happened, the hurricane, it wasn't that there weren't enough supplies, the communication went down. And that causes more chaos than anything else. If you have an asset like ours that's flying persistently nonstop, is able to daisy chain as well as create backhaul of data within itself and extend comms networks such as wireless services networks, you suddenly are taking care of an extremely critical piece. You have a cell tower in the sky flying. The look down angle of that cell tower is going to be way more effective than any ground-based cell towers. While it's also doing the detection, utilizing other payloads and sensors on board and doing edge computing. This is when you're talking about game-changing robots truly coming in and actually assisting in what we're talking about in terms of managing disasters. Subsequent to the disaster and subsequent to actually being able to assist first responders in managing the disaster, there's search and rescue. Effective search and rescue. Today, we were working with the Custom and Border Patrol as well to help save lives of people being lost in desert, as well as during these disasters that are happening. Actual differential in temperature allows us to detect humans faster or any kind of life faster and be able to fill that back in. In addition, provisioning the wireless services to essentially ensure that comms isn't broken truly helps with the search and rescue. And then geolocating everything that we're doing so that you know precisely where and when to send help in order to save lives. I'm going a little quickly so that we also get time for some of the questions. Post-fire assessment is equally important, or post-disaster assessment is equally important. So essentially, early detection during the disaster, managing the disaster, and search and rescue efforts. And the third is post-disaster. We were talking to the state of Tennessee when they had the tornado, and they were looking for aid from FEMA, and actual assessment of the damage so that proper funding could be provided was a critical component. Being able to cover large areas so that you're able to fully assess the damage, determine what would be needed from a funding perspective to rebuild, and then monitor the entire rebuild process so that it can effectively and efficiently be brought back up is critical. And if you have long endurance assets that are fully autonomously flying, you're able to do that, again, cost effective and efficiently. Now, that is the entire disaster management, and having an asset that is a fixed wing asset beyond line of sight, fully autonomously, with the capability of edge processing and doing machine to machine, human to machine teaming, which is critical. Because when you look at, so as an organization, we've looked at nature to feed in a lot of the technology advancements that we've done. For example, long endurance flight. When you see birds flying long distances, they're not constantly flapping their wings. They use environmental conditions to actually fly, which is, example is thermal, utilizing the hot air rising. Similarly, our asset utilizes multiple energy sources, one being photovoltaics or solar panels, the most sophisticated solar panels that exist, space grade, that we utilize to create surplus energy on board. In addition to that, we utilize thrust only 10 to 20% of the flight time. So essentially, when we detect a thermal, we are able to identify the center of it and utilize that for flight. However, we don't compromise a mission for that. So what Davide said, if we had to fly fast to a particular location, we're able to do that, bypass the ability to locate. But if we had to station keep long durations on a certain area and be able to swap that area, we'd be able to utilize environment conditions like orographic lift and others for our flight. And that allows us this long endurance flight component. That is when you truly become a pseudo satellite that does not need orbit, and create constellations of multiple of these assets flying and swarming together like insects to be able to complete a mission. And so that actually, I'll end at some of the components of how you need to look at this in a way where this is a multi-layer, multi-altitude problem that we're all solving. Ground-based robots, you have assets that are flying in the aerial space. And then eventually, as we are designing higher altitude assets that are flying in the stratosphere, that truly come in between the orbital assets and aerial assets to capitalize on the stratosphere where there is actually no aerial or commercial air traffic, and you can truly create constellations without orbits. And so that's what we are currently designing, and we're flying the ultra long endurance. And I'll actually show you a quick video to give you an idea of what is some of the work that we've already done and accomplished in this space. So give me a second and I'll share my screen. I'm hoping you guys can see the video screen now.
Yes.
Hello? Okay, awesome. So I am going to extremely operationally efficient. You can deploy it anywhere off of a rented SUV or any kind of asset that you are driving, or even put two bungees and launch it. This is when it has detected a thermal and is able to fold up the prop and fly on its own. And fully graphically mapping the entire area of operation. We've already done this flight, is what I was mentioning earlier. I'll stop sharing that and hand it back to you, Bilal.
Thank you, Fatma. Impressive stuff, really cool. I see many questions coming up on the Q&A to all the panelists. And I see also that some of our panelists have taken the time to answer some of the questions. So let me perhaps start with a few questions to kind of kickstart the discussion. Perhaps going back to Dr. Murphy, what's the biggest challenge we foresee in developing these robots for disaster response and reconnaissance?
So reconnaissance is certainly one of the big missions. There, for drones, we find that there are 8 major missions. Reconnaissance is one. The biggest challenge is actually not a distance challenge. You have a very high density of airspace, so you want to keep an eye on it. You know that. The biggest challenge we actually see is that the responders, the emergency managers, don't know the capabilities. So they don't understand what drones can do and how much value that they can add them. So I would say that's the biggest problem. A second challenge we do see is communications. And Fatima referred to that there in as well as Davide. The streaming communication, typically when you're doing reconnaissance during the response phase, you have an expert, a drainage expert, a levee expert, a bridge expert, a tactical search and rescue expert with the piloting teams. And they are able to look and say, yes, there, no, left, yeah, over there. Well, that's great, but none of that, often there's no way to stream that critical picture back to someone. A lot of times they use email on their list. And so getting that communication of what is the right information And we've seen disasters where people try to send everything to everybody, just totally clog the networks. And so prioritizing who needs what when. At Hurricane Harvey, we actually had a courier system where the teams kept pushing forward, but there was a person driving to each of the 17 groups pilots to get their SD cards and bring them back. So as well as calling in on the radio, the findings. So you got a yes, no from the experts of what was going on or what was needed. Anyway, that was a little long, sorry.
No, that's great. Knowledge or being new, the rescue workers are not familiar with this new technology. So sort of capacity building in that space might be helpful as these new robots and technologies are brought to disaster zones. And as you mentioned, the communication, having the right communication and the right information to be shared is important during that critical time.
And we do free training for emergency managers, so we can do online. So if any of your groups are interested, CRASAR can do that. So just
fantastic.
throwing that there, sorry.
Okay, well noted. Might take you up on that offer. Let's see. The next I'd like to ask Professor Howie, what's your greatest challenge in employing technology-based assistance during disasters?
Yeah, I don't think I can point to something and say that there's the greatest challenge. Making the tool work is a challenge. Getting acceptance for the tool to work is a challenge. Getting knowledge that the tools exist is a challenge. Getting knowledge as a need for development is a challenge. Sometimes I jokingly say with one of my colleagues, making the robot's not the hardest part. Getting the funding for it too. Within any of these categories, and I suspect you were asking about the technical challenge. Mm-hmm. Again, no one technical challenge. Mobility is hard. The mechanism design is hard. The controls, the perception, all these things are hard. And then why are they hard? Just pick mobility as an example. You want to be strong, maneuverable, and small, and those are fundamental, and not hot. And those are all fundamental trade-offs that we have to fight with. For control, you have all these degrees of freedom. You have unmodeled disturbances. Again, very hard. Planning. How do you figure out not only go here, go there, but use this part of the environment as an affordance and that part of the environment as an affordance? How do you know this part isn't stable or unstable? And that gets to perception. So yeah, I can go on and on and on and on. And I'm hoping people out there listening to this have a whole bunch of interests that can serve any one of these. And then the final technical challenge, of course, is integrating all this stuff together.
Mm-hmm. Well, the interest is certainly there. We see close to 200 participants live, many questions in the Q&A. There are questions related to the capabilities of these robots in terms of the time autonomy. For example, for some of the UAVs. So there is question about the autonomy, how long they can fly. Perhaps that's related to the battery life and also the range and the distance. Would anyone like to address that question in terms of the capabilities of the UAVs?
So, Bilal, I can take it from a UAV perspective, and I'm not going to comment on the rotary devices, but more fixed wing. Essentially, endurance, which is how long it can stay up, is, yes, the function of the energy available, the power available for recharge of batteries on board as well. And that's where it's not just about the battery life, which the battery technologies now are really advancing. Simultaneously, as I mentioned earlier, we have attacked it by doing a multi-pronged approach, not just creating surplus energy on board, which recharges the battery constantly, but also utilizing, so our aircraft are glider aircraft, so you can actually utilize wind and thermals to fly without needing the power. But when you look at UAVs, it's not just the energy or the power needed to fly, but it's also when you look at edge processing capabilities, communication or radio capabilities, how are you actually providing power for those components on board becomes critical, because it's not just about how long you can fly, it's what else what can you do while you're flying that long distances or long endurance. And then distance there is a function of, as we call it, command and control, C2. How are you actually flying these assets? Can they fly without fully autonomous assets? So if they lose link with their operator, how are they operating? Or if they lose link with GPS navigation, how are they operating? So that determines a lot of the distances they can fly, along with obviously the endurance component of how long they can fly. And so it's a multidimensional problem that, so for example, we've addressed. We can go thousands of miles. It depends on where we're flying, the conditions we're flying, and also when and how the data is going to be brought back. And then that's where I had mentioned daisy chaining. If you have persistent assets that can do backhaul of data or connect back to the satellite and do backhaul of data, there are multiple ways of skinning the cat, and none of us are going to skin the cat here. But yes, it's so I know that was slightly long-winded, but hopefully that addresses some of the questions.
Thank you, Fatma. Would any of the other panelists care to comment on that question of capabilities in general of these robots and UAVs, etc.?
So I can add about the endurance of quadcopters, hexacopters, and so on. So typically, depending on the payload that they are transporting, basically the takeoff mass, the endurance ranges from 10 minutes to 30, 40 minutes. But it also depends very much on whether they are flying against wind and on the type of trajectory that they're flying. So for example, if they're flying a straight line, typically that's how actually all the commercial drones companies actually measure the typical endurance. So a straight flight without any wind. So that's what you see usually in the data sheet. Then of course, if you have a twisted trajectory and then you even have a wind or other type of disturbances, then the endurance drops by a lot. I would say that, for example, in terms of autonomy, for me, what is actually more important is not really much the endurance, but how much you can actually accomplish within the limited battery time. So if you know that your budget is 10 minutes, try to fly as fast as possible within those 10 minutes. So if the goal of the drone is to actually do 3D mapping, try to 3D map the whole floor within those 10 minutes. So that's why I'm actually arguing that I'm working and I'm arguing actually we should work more on agile autonomy rather than on standard, slow autonomy. Try to get these autonomous drones able to fly very agilely, okay, very fast.
Okay, great, Davide, thank you. So maybe let's move on from the capabilities to, there is a lot of algorithmic research that was mentioned in various presentations. For example, the Ergotic search algorithm. Professor Howie, there is a question if you could say a little more on that, and maybe if they have any references to point the community to. Professor Howie, you're on mute.
There we go. So I was very brief with my explanation in my talk, but essentially what Ergotic search does is it takes what information you have, say an information map, and it optimizes where to search based on the most likely locations where some target may be, but recognizing that there still is uncertainty. So if you concentrate all of your search towards only the high likely locations, you are going to miss something. So Ergotic search makes that exploration versus exploitation balance for you. The people who pioneered this work, the first person, his name is Igor Mezic, M-E-Z-I-C. He's, I think, University of Santa Barbara. And then the next, University of California, Santa Barbara. Then the next person, his group is Todd Murphy, M-U-R-P-H-E-Y, a different spelling, or as Robin Murphy would say, a misspelling of Murphy. And then the person after that is me and Ian Abraham. And Ian is now a professor at Yale. His last name is Abraham, like Lincoln, Abraham Lincoln. And what we can do is, if you Google my name, you'll find references to that work. In fact, I think DARS this year, it's the premier multi-agent systems conference. I think one of my students' papers was actually won the best paper for that, and I think it's a good exposition what's going on there. And I should also acknowledge Guillaume Sartoretti, who's a professor at National University of Singapore. So one thing you all should be seeing here is that I like to eat my young. So once they leave me, I still work with them forever because they're great and they let me stay with them. But those are all good citations. My name and the word ergotic search as a Google search will get things. And if you want, we have slides and pictures and stuff that we're happy to share with you. And we have a weekly ergotic search meeting. And if anyone wants to, you're welcome to join that.
Very good. Thank you. Thank you very much for that. Any of the other panelists would like to chime in on the discussion around algorithmic research, advances, search algorithms? I saw in a few of the presentations, what's the best path to take to have these assets work together? Any points on that? Fatma?
So, Bilal, I won't comment on the search algorithm, but I will comment on the machine-to-machine and human-to-machine teaming, which swarming, we refer to as swarming, and swarming has different meanings in different places, but essentially that coordination, right? How are you, and so there is an aspect of communication that comes in as well. So for example, we fly a radio bridge. That way, if somebody is connected on a certain waveform, as long as they connect back to us, we're able to connect everybody who's on, even if they have different waveforms in terms of radios, and are able to disseminate information. So when you are coordinating the communication component, as well as tipping and queuing, so if you're collecting certain amount of data, and then you have to hand it off if certain criteria happens. And those are the components that we're also training in the back end so that we can effectively do tipping and queuing between different assets and ensuring that communication and data exchange between assets utilizing different technologies is enabling. That's how you're also going to be able to solve for some of this.
Excellent.
I want to do step in here.
Sure.
Is that there's really two aspects that we see in managing a disaster. One is strategic, which you think of the big picture, all that information going to people in a control room and making important decisions. And then you have the tactical boots on the ground, people in the mud, pulling other people out, putting them in boats, where that. So a lot of the communications and things are back to the strategic level of management. But don't forget having a drone in your pocket, in your cart to pop up to tell you what's the best way to get to that person on the roof, or where are their other assets, or things, or overwatch, or what is the extent of the damage is also very valuable, but has a different communication demand and is less likely to require swarming because it belongs to that person. It's on demand. One of the problems we see with strategic assets, and one of the things that made the small drones so exciting for responders, is they no longer had to depend on the helicopters or the Civil Air Patrol and then say, could you please look over here? And the answer was usually no. And, we're busy doing something else, or we've got to do this other big thing first. So being able to have that on demand. So we really want to see heterogeneous solutions and heterogeneous control. So don't think you have to have something that you need all of them, but they all have different places they fit in.
Great. Maybe to pick up on that response, Professor Murphy, what are the usual communication protocols used in these various, both strategic and tactical? Are we using satellite, cell towers, Wi-Fi, mesh networks? What are the various options that are being used today?
All of the above. Mostly, though, we see we use cellular. Most agencies can't afford the satellite connections. What you try to do is that you hope you get some cells on wheels, cows, as we call them in the United States, into the site. Usually there's a commercial pressure to get them in very quickly. So you see those. There is a big investment in the United States for what's called FirstNet. Fatima talked a little bit about that, which gives priority over the cellular network to responders. But it's a cellular network, and what they've discovered, and we're a big FirstNet school, is that the assumption was it was about downloading data. So the downward link is better than the upward link. But what we're finding in real life is that if you're trying to do mapping, or you get this great video that explains what's going on, like at Hurricane Ida, that all of Grand Isle is wiped out. Now you've got the uplink, and that tends to be much slower. So some of this we're learning as you go.
Okay, anyone else who would like to add to that in terms of the communication protocols? There is a related question also on the bandwidth available in these various channels, and whether that's sufficient to stream the images during flood management, for example, from Dr. Shukla.
So during flood management, we do a lot of floods. The nice thing about floods is that your cellular network is intact for most cases, right? And so that has worked out very well. And that becomes a matter of things like streaming, back to the command center. And we did that at the Kilauea volcanic eruption. So that is certainly a possibility. We do try to emphasize that streaming may not be always useful. And in fact, if you look at the cognitive studies, people in the incident command already have a problem of watching CNN or the news or Sky a little too much, that they don't pay attention to what they're supposed to, because we're built to look at moving stuff. So what we find that streaming in the field often is at exactly the wrong time. So we're up in the air streaming, and everybody else needs to be doing something else, or it's too much and it distracts them from what they're doing. So you kind of have to play that by ear on what is important, and to synchronize with what the incident command needs. Fantastic.
If any of the panel want to chime in, please do. Otherwise, I'd like to move to the next question on the data. One of the panelists mentioned that the simulation is being used to generate the data to train the algorithms. Could you comment on the various data, that is types of data needed in this space of robotics for disaster management? What are the sources of data? What's the quality of data? Is there data commons where various researchers and groups working on using robotics are sharing that data? What are the things do you have any calls for action on that, in that space? Over.
Wonderful question.
Very broad question.
Okay, yeah, I get the question. So first of all, let's remind that let's remember that autonomous navigation is still, not really deployed in search and rescue, especially, inside buildings and so on, because there are still a lot of problems to overcome. So it's still an open research problem, especially if you want to fly fast. Now, though, that's why actually the whole community is relying more and more on simulation tools. So the simulation, the simulator we use is actually Unreal Engine, which is actually used to develop video games. And that's actually the beauty about using video game engines. The amount of scenarios, we are talking about thousands of scenarios that are available for just $20 to $50 US. You can download them. We are talking about several kilometers of scenarios that you can actually use to train these algorithms. Also, what you can do is that some of the scenarios allow you to randomize some the size, the density of the obstacles you want to simulate. For example, for the training the algorithm that was deployed in the forest, we actually downloaded different type of forests from Unreal Engine, and then we randomized the diameter of the trees, the density of trees, the orientation of the trees. We also added a lot of rocks and so on. You can also play with the illumination, some other kind of visibility conditions, although they are not really realistic. And now that's where we actually are hitting the ceiling. Now, if you want to really train these algorithms in simulation and then deploy them to the real world, there is always going to be a simulation to reality gap, but due to the fact that basically you cannot simulate everything. So eventually, as Robin said, the latest test is always to run it in the real world, and especially in realistic conditions, so in the real fields. However, robotics is very difficult. Autonomous robotics is very difficult. So I would say that, for example, in the autonomous driving community, I see that companies are making giant steps. So they're investing tons of money in making a realistic simulation of the weather conditions. So I read a paper from BMW where they're trying to actually try to simulate, for example, the raindrops, fog, and so on, in order to train their machine learning algorithms in these conditions with the hope that they will work in the physical world. Again, it's still a hope, but the reality is that we need tons of data. And also, another thing that we need to do is to actually try to simulate realistic scenarios into the simulator. So meaning going to the fields, getting data from the search and rescue operations, possibly using LiDAR in order to build even more realistic simulators. Because the reality is that in the end, you will need a simulation in order to do parameter exploration. Parameter exploration is one of the tools that we use in robotics in order to tune our algorithms. We have hundreds of parameters for our algorithms. And usually when we train these algorithms, so we select the parameters that are optimal for a given task, they may be suboptimal for another task. So ideally you should have, a large amount of data sets so you can actually tune in all possible conditions.
Thank you, Davide.
And I'd like
Robin?
to jump in on this one too.
Yes.
Absolutely. But I'm envious of working with computer vision because we know how to simulate that, and all that beautiful work on ray tracing really pays off. When we start looking at ground robots trying to penetrate rubble, all of a sudden we have lots of problems. If we start using active sensing, you're not in a wide space, you're very close. It may be covered with dust and sheetrock, but metal, a shiny side of an appliance sticking up, but at the same time, a rug or textile that typically absorbs the signal, all of these things, and it becomes very, very hard to model. And that's so if anybody's looking for a challenge, trying to model rubble and the heterogeneity and the impact on active sensing is really a challenge. And, but fortunately, we're learning a lot from the great vision work.
Great. Thank you for those answers. I'd like to have about 10 minutes left. There are a number of questions related to developing countries and the applicability of this great technology that is being applied in the US and other developed countries. I think a number of questions are related to how to involve developing countries in Africa or elsewhere, and how much of this technology is applicable in disaster relief in those developing regions.
I guess you can tell from our silence, that's a hard question.
It is. I think drones are very easy to adopt in terms of economics and in terms of use cases. They add a lot of utility, a lot of multi-purposing, and they're easy to use and train, and they're very reliable. Again, you're talking about $1,000 or less. So that works out pretty well. Water-based systems, those are a little more expensive, and they may have different levels of utility. Ground robots tend to be more expensive. But I think if there's no reason for a country to not be able to adopt drones, I think they need the way that we've seen adoption work best in different communities here in the United States is to have the fire rescue department or the emergency management department be the advocates and then explain to the community or explain to the legislature or regulatory agencies and get the political support, because a lot of people look at drones as something that does police surveillance. And so as soon as they start seeing how it's used for wildfires, how it's used for flooding, how it's used to help prevent things, not just respond, everybody's like, well, why aren't we using this? But getting that to them is really important. I think a first step.
I'd also like to add,
Well,
I'd also like to add, when you're looking at persistent fixed wing assets, there is an aspect which I'd refer to airspace deconfliction. And various different countries have their own equivalent of FAA, which is the airspace and international airspace is done by ICAO. When you're operating with different assets flying at different altitudes, and how do you deconflict? So for example, South Africa, airspace is extremely hard to get permissions because all of the regulators are also coming on, just kind of wrapping their heads around. So while we build out the technology, education, not just for the operators or the implementers, but education for the regulators is a critical component, because we need to work together from a regulator's perspective. When we talk about regulation, there's also, as we look at communication, and I'm kind of jumping a little bit, but there is regulations around that too. Collection of data, there is regulation around that. If you collect data over Germany airspace, there's a whole different set of regulations versus collecting data over Botswana. And simultaneously, if you're providing communication or wireless services, there is aspects of spectrum and deconfliction that happens when you are flying. So if we are flying a cell tower at 1,000 feet above ground level, which is AT&T, there is a deconfliction that needs to happen with other wireless providers. So that is where partnering with the right kind of partners that know how to navigate all of these components and not just the technology aspect of it is key and critical.
Absolutely. And we see that multi-stakeholder dialogue taking place at the focus group on AI for natural disaster management in the ITU. And we see a lot of participants from developing countries. So I would take the opportunity to invite the folks on the webinar today who are asking those questions to perhaps join us in the focus group and have that dialogue on not only the technology and how it's being developed, but also on the regulatory aspects, because we have many regulators of at least the telecom sector who are very active in the ITU. And you mentioned a few other regulatory aspects in terms of the airspace, the data that could be collected from these robots and UAVs. So that might be another forum to engage developing countries into this dialogue. I'd like to perhaps conclude with a question on the ethical aspects. I think Dr. Murphy mentioned a few items from her presentation or from the paper that you published. Any other considerations from you, Dr. Murphy, or any of the other panelists?
The biggest ethical consideration I have is that robots are so useful. It is unethical not to use them. That if we had, this is like saying we have penicillin, but let's study it more, or we have a lot of regulations. No, it's time to start using these technologies because there are so many good uses. So I think the biggest ethics is that we're not doing what we should be doing with it.
Thank you. Anyone else?
Yeah, I just want to second Robin's comments. I like how she said it.
Great, thank you, Howie. Anyone else? Any final comments from our panelists before we wrap up? You want to take 30 seconds in terms of closing remarks? Please go ahead. David? Fast. I noted that it has to be fast during the period of time. Strike when the window, when the iron is hot is certainly a key message. Fatma?
I think I'll echo what Robin said. Not deploying these is criminal.
Okay, excellent. Ladies and gentlemen, I'd like to really thank you very much for your participation and for all of your insights today. From today's discussion, it's evident that robotics is increasingly being recognized as a significant tool, not only for disaster response and recovery, but also for disaster monitoring, prediction, and mitigation. With the ability of these robots and UAVs to gather data and perform tasks that human operators and equipment cannot, they're able to reduce disaster risks, rescue time, and cost. The next step in cementing the promise of these technologies is to explore their use through the lens of standardization. And I would like to invite you to follow the work of the ITU WMO UNEP focus group on artificial intelligence for disaster management for more insights on this. Before we close this webinar, I'd like to thank you all for your unwavering attention and participation. Also like to express my gratitude to our panelists for engaging with us on this relevant topic. Thanks once again to our panel, our participants, our partners and sponsors, and I hope to see you again soon. Stay safe. Thank you.
Thank you very much, Bilal, and a big thanks to
Hey, thank you.
Thank you very much, Bilal, and a big thanks to all our panelists, Howie, Fatima, Robin, and Davide, as well as to all the participants for making it such an interesting discussion. We had lots of great questions and many examples on how AI-powered robots are being deployed for disaster preparedness and response. We are now opening a quick poll with one question. Please answer and let us know how much you like this session. We also encourage you to check out the AI Focus program online to see more sessions that may be of interest for you. For example, tomorrow, Wednesday, we'll have a discovery session on AI and weather and climate, doing better, doing different. On Thursday this week, we'll have a session on algorithmic recurse from theory to practice. And finally, on January the 20th, we'll be discovering robotic exploration of subterranean environments with Kostar Alexis, Professor of Robotics at the Norwegian University of Science and Technology, Navinda Kodech, Group Leader and Principal Research Scientist at C0 Data 61's Robotic and Autonomous Systems Group, Ali Agha, Principal Investigator and Research Technologist at NASA, and moderated by LJ Reed. With that, we have reached the end of this webinar, and we would like once again to thank everyone involved, our panel, our participants, partners, sponsors, and co-conveners Switzerland. Thank you very much, and hope to see you again very soon.
Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Rewind selector. Rewind selector. Rewind selector. Rewind selector. Rewind selector. Rewind selector.